Hi, for those of you already on the line, we'll be waiting just another couple of minutes before we get started at the top of the hour. Thank you. Hello, everyone. Let's go ahead and get started. I'm Charlie Smith, Principal Consultant with ESIG and Co-Pillar Lead with Mark O'Malley of Imperial College on Pillar 1 of the G-PST. The mission of the Global Power System Transformation Consortium, or G-PST, is to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. At the core of the G-PST is a large cross-section of system operators from around the world who are dealing with a rapid transition from a system based on synchronous machines to one built around inverter-based resources. The 5 pillars of the consortium include research and peer learning, technical support, workforce development, standardization, and open data and tools. More information on the G-PST can be found at globalpst.org. As the co-lead on Pillar 1, ESIG would like to welcome you to the October monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is an addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both system operators as well as members of industry and the research community. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, lines will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we will use the Slido platform at slido.com. To ask a question, please navigate to slido.com and enter ESIG20 as the event code. The instructions are also at the bottom of the screen. You will see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 5 or 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, So please don't be afraid to ask your questions through Slido. Today will be presented by a team from the German TSO 50 Hertz. 50 Hertz is well down the path of renewable energy integration, with an average annual infeed of around 75% today, and expecting to integrate an annual average of 100% renewable energy by 2032. In order to achieve this goal, 50 Hertz is developing a next-generation control system, which will be the brain of their renewable integration and is referred to as the MCCS, or the Modular Control Centre System. The key words for the MCCS are flexible, scalable, and adaptable. Today, we will explore the components of the MCCS grid analysis suite, products which will be provided to the operators in the control center. These products include dynamic security assessment to ensure stability, topology optimizer to avoid congestion, and volt control to manage voltage. Today's webinar will be presented by a team from 50 Hertz, led by Arya Fazilat, the project leader, and 3 of his team members. Arya will be joined by Michel Gerold on grid analysis and dynamic security assessment, Christian Merz on topology optimization, and Dominique Wassermann on volt control. I had the pleasure of participating in the 50 Hertz annual checkpoint event dealing with the MCCS last month in Berlin, where I was able to catch up with Arya and meet some of the team members. 50 Hertz has participated in previous webinars with us, and I'm pleased to welcome them back. 50 Hertz leads the G-PST Control Room of the Future Implementation Council, is a good member of ESIG, and Arya is a good friend. This is a very unique and groundbreaking effort in which they are involved, and I look forward to hearing what they have to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG20 to ask your questions. Let's go ahead and get started. Arya, I will now turn it over to you.
Hello, Charlie.
Hello, Arya. We can hear you.
That's a good start already. Let me just share.
Yes. Okay.
Okay, now you should see the screen, right?
Yes, we see full screen now.
Okay, great. So first of all, thank you very much, Charlie. Thank you to ESIG and G-PST. As 50 Hertz, we are a proud member of the G-PST community. And as you said, we had a great event in Berlin just around a month ago with over 250 people from the system operations community, from academia, from research, from startups, and from the industry to discuss the challenges and opportunities of working together in the sector of digitizing system operation and digitizing the energy transition as a whole. And today, the colleagues and I will speak about the grid analysis suite of the MCCS and how we address voltage, stability, and congestion issues. I will start right away. So we go a bit through the background. We will tell you where we come from, what do we do as system operators, and then we will jump into the grid analysis suite and go into the products that we have, the state estimation and security analysis, the real-time optimization, the voltage control, and the topology optimization. And if you have any questions, of course, use the Slido, but feel free to reach out to us after the webinar as well. We always look forward to exchange with colleagues and to cooperate. Let's start with the background and context. I keep it short. We are a group of transmission system operators at the heart of Europe. We are based in Germany and Belgium, Elia for Belgium and 50 Hertz responsible for Germany. Transmission system operator, our job is to plan, build, operate, and maintain the transmission infrastructure, and we have the goal of integrating 100% renewable energies into our grid. Currently, we are around 75% renewables. That's the background, and I want to start with some positive messages here. The outlook for system operation were very good news. The share of renewables are increasing, and they have increased a lot. What we see here, solar PV, onshore wind, offshore wind. So I think we're a good trajectory where we see what happened in Germany from the 1990s to today to 2025. And going toward over 300 gigawatts of renewable energies by 2030. So that's a positive message for the affordability, for the sustainability, and also for the security of the system in the long run. And having said that, in the medium term, there are some challenges for us as system operators. What you see on the chart, this is what we expect for an average week to look like in 2030, so in 5 years' time. And you see our load, what we call last, with a grayish chart, and you have incredible peaks of solar PV during the day. And of course, this will create some challenges for our system operators for stability, voltage, for the optimization of the topology. So many good news and for the system overall and for our societies, but also with some challenges in the medium run. Basically, we cannot operate the system of today with the tools of yesterday. And as 50 Hertz, we have recognized this problem and this issue a few years ago where we started our digital transformation journey. We believe that digitalization, automation, and the support of our colleagues in the control center with digital tools is key, and it's a necessity to keep our job of keeping the grid and the lights on 24/7. So usually we have this framework of the 3 pillars. Today we focus on pillar 3, but just for the colleagues who are watching and who want to reach out afterwards, I give you a brief intro. So our digital transformation journey started with the objective that we want to become a digital system operator. And that means that boldly we started to build our core IT, which is the control center software in-house. For corporate IT and office IT, we adapt and we use standardized IT, but we really build our core IT, the control center system software in-house. And in order to do this, we have undergone and we are still in the process of the digital transformation. And in terms of organization, that means that we set up a product organization. We've started with 3 people and now we are over 150 people whose day-to-day job is to develop software for the control center, and software meaning functionalities for the control center. So we are 150 people in this product organization that develop the modular control center system. In terms of technology, and that's the focus of today, we move from a locked system, a monolithic system, to a modular integration platform where you can plug and play different modules. And the grid analysis suite is one product line and with different modules, what we will present today. And the 4th pillar, it's very important, and that's why we're here today as well. We believe in this ecosystem approach where cooperation and co-creation is key. We don't want to build everything alone. We want to exchange. We believe that all the system operators, whether you're an ISO, a TSO, a DSO, we need to reach a new level of digital maturity. And that can mean that you have a product organization developing software or integrating new kind of software tools, but we need to be in constant exchange. And as you mentioned in the beginning, Charlie, we had a huge event, a successful event a month ago, and we will have it again next September. I think in the 2nd week of September, the so-called MCCS checkpoint and the Global System Operations Summit. So please reach out for us as well on this one. So together we can shape this ecosystem where you have system operators dependent on a one-way street towards creating a more dynamic ecosystem where we can share and co-create different functionalities and modules. And Christian will say a few words about that as well, because the topology optimizer is really a product that came out and that harvested the benefits of that co-creation. Last slide on my side. So what I told you, our vision is, and we are developing the modular integration platform, which is the integration platform using Kafka with a central governance scheme for security and data. And on top of that, we build functional services. So these services are core functionalities for the control center, and we don't want to build everything ourselves. So for each functionality, we make a make or buy or cooperate decision. At the moment, we are developing the monitoring and control parts for our grid and the energy management system. Today, we have the grid analysis suite as well. We are developing functionalities there and forecasting. But there are also some tools that we cooperate with our partners and some tools where we follow the traditional approach where we use the market to get our access to the functionalities. And this plug and play system gives us a lot of scalability and flexibility and creates really this dynamic market. Just on the side, what you see here, important topics that we can discuss, that you can put in your questions, but we can also take it another time. Data is key. Data is very important. The reusability aspect, security, open source is an important topic. Christian will mention it, and artificial intelligence, of course, as well. But it all starts and ends with data, to be honest. But I'm sure we'll get some questions there. And that was my introduction already. And with this, I hand over to the grid analysis suite. So you can imagine it as a big building block with many different smaller blocks and products that serve as functionalities. And with that, I hand over to my colleague, Michael.
Thank you, Arya. And also thank you, Charlie, for the introduction. My name is Michael Gerold. I'm currently the acting product line lead of the grid analysis suite and also the product owner for the dynamic security assessment. And now, after this broader picture that we have seen, let's funnel through and get more specific into the grid analysis suite. But first, let's start with our goal. So what are we planning to do? Next slide, please. Our goal is to build a user-friendly analytic tool that improves the decision-making of power system operators. And how do we want to achieve this specific goal? On the one hand, we have one advantage. Our users, our operators, and other users such as data experts sometimes are sitting right next door. And so we can work with them to develop the tools that will make their life hopefully easier. And on the other hand, now we can move to the next slide. It is by how we build our grid analysis suite. So as Arya has already told us before, ever larger networks, more assets, and also new phenomena that we perceive in the network pose new challenges for our operators. And what we want to do is we want to solve these challenges with flexible and performant tools. And what does this mean now? It means conventional solutions, what we've seen, they run usually sequentially. Only after one analysis run has been conducted does the next run start. And however, our approach allows different analysis processes to run even in parallel. But to actually ensure high flexibility, we can also change the order of different tools based on the requirements of the operators and based on the use cases that we can see and that we can predict. But for us, it also means that flexibility is even more than just that. We also offer an open platform so that we can use the right tools for the right tasks. And this ability to implement different frameworks, both open source or commercial ones, interchangeably allows us for specific and future-proof solutions, depending, as I mentioned, on the problem that we face. And this is our vision. But now let's take a deeper look at the current state of the grid analysis suite. Currently, we are pursuing what we can see on this image. We are pursuing a dual data approach. That means on the left-hand side, we can see we can use our own MCCS data format, but also we can use the CGMS standard data format. This allows us also, so this dual data approach allows us for even greater flexibility in the development of our tools, because as we connect our tools, we can use also the existing systems to validate whether our developments are running in the right direction or not. And also in addition to this dual data approach, we also follow two analysis paths, one in real time and one predictive analysis path. And the first step for both paths here is the creation and the validation of the grid models that can be calculated by our tools. And this path, after this first step, forks. And there is one fork, this is the orange path, which describes the real-time process path. This always starts with the state estimation, which we will talk about just in a minute. The results of the state estimation, it is the input for our successors of the state estimation or successive processes of the state estimation. This is the security analysis and also some real-time optimization, which, as I mentioned, uses estimated values as input. The other, the predictive path, forks to the bottom of this picture to the preventive optimization tools. They don't use this estimated values. They use the CGMS data or the MCCS data directly for the forecast, so the forecast values there. And all these tools, so the security analysis, the real-time optimization, and also the preventive optimization, they create predictions and they create remedial actions for the operators. So it could be either switching or other control measurements that can be recommended for the operators, who has then to decide whether to use this or not. And now let's move to the first more specific tool. This is the state estimation. And the MCCS state estimation is providing operators with a real-time and reliable overview of the electricity grid. And as we heard before, the energy landscape evolves with more renewables and distributed assets added to the system. Achieving this comprehensive grid visibility becomes increasingly complex. Multiple data sources are one of the reasons, but this can result in gaps or inconsistencies in the information that is available to the operators, which makes it challenging for the operators to make fully informed decisions. And to address these challenges, the MCCS platform collects, validates, and harmonizes real-time grid data. It ensures that operators have the most accurate and up-to-date picture possible. And even when some data sources are imperfect, advanced algorithms, which we are using here, can still deliver robust state estimations. And this enables operators to make more secure and timely decisions backed by insights and the understanding of the grid's current state. And now I talked a lot about what is actually happening in the state estimation. Now let's take a first look at the system. And for that, give me one moment. I will share with you one of my screens. So now you should be able to see my screen. And the first thing that you can see here is the login screen to the MCCS system. You can log into the MCCS system either by typing in your username or email with a password, or if you're an employee of 50Hertz or Elia, you can also use the single sign-on, which makes it much easier for me in this presentation now. Okay. Second time works better. When I'm opening it, we can see the last screens that I used beforehand, but we don't want to look at the GIS overview that we can see here, or the energized or de-energized states of the network. We want to open the burger menu where we can see all the tools that we are currently showing in the MCCS toolbox. It goes from the assets, from data management, over the forecastings and outage planning to the grid analysis toolbar. And opening this grid analysis toolbar, we can see all the tools that we have currently in the MCCS toolbox. We can see that we have oftentimes the CGMS and real-time data suffixes. This is based on this dual data approach that I was talking before. And now I want to show you the screen, which basically is showing the results of the state estimation. This is the discrepancy list. Here we can see the discrepancy list for the full 50 Hz control area. It is based on the CGMS data that we are getting from another software that we are currently using. And the conducted state estimation results are shown, as I mentioned, in this table. What we can see here is the ID, the element types. We can see on which side of, for example, a transformer, we can see this estimated values, either the high voltage side or low voltage side. We can see the type of the measurement that we can see here, the sigma value, which helps us to assess the error margin that we have for specific components. We can see the measured values in this column and then the estimated values in the next column. And we could see sometimes they look a little bit off, but what we also are doing is we are also comparing our estimated values here with the estimated values of our inventory system, of our current system at 50 Hz. And so we can see that the deviation margin between our tool and the tool and our current operating tool oftentimes isn't as high as predicted. And to give our users, especially here, the data experts, a better understanding and a better overview over the current state estimation results, we also have this visualization of the deviation. This deviation is based on the sigma value that we have, so it's not the direct deviation, but it's a formula that is behind that. And here they are ordered based on the deviation that we can see. Usually such big deviations, they would mean two things for us. Either our state estimation is wrong, and so we have to tweak the state estimation that we are using, or it could also mean that the measurement values in the field are bad. And that would also mean that for the data experts that there are some further actions that they have to take here. Now, let's move back to the slides again. We will jump to the first tool that uses this estimated values. And this tool is the security analysis. And with the security analysis, it is designed to simulate and assess the grid's resilience to potential failures, enabling safe and reliable operations. And by providing timely detection and mitigation of risks, this process helps operators to maintain the control even in difficult situations. Because we know that the operators are stressed or in difficult situations, they usually get stressed. So it is important also for us to have a clear visualization that we develop here with our operators together, with their experience, and it should help the operators to efficiently interpret the results that they see there and make quick decisions. And this analysis highlights that a single unnoticed fault can escalate, potentially leading to widespread outages if not promptly addressed. And maintaining grid stability after the failure of just one component outage, and this is the N-1 criterion, requires careful and complex assessments. And moreover, unusual events or combinations of outages, they demand even more attention and rapid evaluation here. And now again, let's move back to the to the system, to the operating system. So I will again share my screen with you. And as you can see, we are still at the discrepancy list, but now we can open again the grid analysis toolbar, and we can see here the 4-quadrant view. Now opening the 4-quadrant view, we waited a little bit and we also see some results here. The first thing that you will realize is that we are currently just depicting 3 quadrants or 3 tables. We are working at the 4th quadrant. I will talk about it just in a minute. So what we can see on the left-hand side, the left table is showing us the current loadings of specific elements in the network. So what we can see here is the specific element. In this case, it is the line 567. We can see the base load that we have here. It is 81.6%. And if the line 568 which looks like a parallel line fails, the load on this line, it almost doubles to 156.8%. What we are depicting here is always for each element here, you will only see it once, the worst outage that can happen. So we can also see the next element. It is the different line. So the other line, the line 568, it also gets to a worse loading value when the line 567 fails in this case. What else can we see in this table? It is also that we are using here a visualization, a color scheme, a specific color scheme. The violet color indicates every instance when we have an overloading, so a loading over 100%. The red color always indicates a loading of more than 90%, but less than 100%. And the orange ones, they are everything that is between 80 and 90%. This isn't arbitrary, the color schemes that we chose here. These are color schemes that the operators know and that and so they can quickly get a better understanding on what is currently happening here. A similar thing we can see on the right-hand side where we see the voltage magnitudes, how they change when a specific component also fails. In this case, we can see usually it is in the green state and the base case that we have here. And on the right-hand side, we can see the voltage deviations after the outage. The last table that we can currently see is the voltage angles. This basically indicates whether we can connect a component to another, because if the voltage angle deviation is too big, it doesn't work anymore. And the last quadrant that we are missing currently, it is the cascading effects that we will show probably next time. And with that, I will hand over to another tool that we can use with the input of the state estimation results. To you, Dominique.
Thank you very much, Michael. My name is Dominique, product owner of optimization and automation at MCCS. Very thankful for this opportunity here and happy to present our work in the MCCS. Let's shift our focus to this area of grid analysis, optimization and automation. As you might have experienced yourself, the landscape of grid operations is changing rapidly. With increased volatility and fewer rotating masses in the grid, our operators face higher and more complex workloads than ever before. That's why one of the main drivers of our development efforts is the creation of tools designed to deliver clear and actionable decision support and automations for our operators in their daily routines. When it comes to optimization, there are two main areas of interest for us at the moment: curative, or in other words, real-time optimization, which allows us to respond quickly and effectively to critical events or outages. and preventive optimization, which helps us to put measures in place to avoid issues before they even arise. But let's take a first look at an example of real-time optimization for offshore wind parks, Optimizer 2.0. In its final state, Optimizer 2.0 is a real-time wind park controller, which aims at operating our offshore wind parks as close as possible to their maximum efficiency, but independently of grid state, which is in this case topology and available wind infeed. Why is this a challenge in the first place? Number one, the number of wind parks we deploy to our transmission grid is increasing, so higher monitoring effort. Then obviously the high volatility of these wind parks causes even higher monitoring efforts. And that essentially leads to the fact that in critical situations, our operators have to take decision in a very short amount of time, potentially, and under a lot of stress. At this moment in time, all of what I just described is a very manual process. So the operation of these offshore wind parks, in short, our operators need to see the situation, calculate countermeasures manually, and send the controls out to the wind parks. And that's what we want to change. But why do we even need to work on offshore wind parks or optimize offshore wind parks in the first place? First of all, offshore wind parks at 50 Hertz and Elia are not N-1 secure by definition. That means the cables that connect the offshore wind park to the onshore, they do not suffice, or they only suffice if they are all available in order to transport the entire energy produced by the wind park. That means if one of the cables is out of service, we cannot transport the entire capacity of these wind parks. That also means we must prevent overloads of these sea cables or reduce them to a very short time span because we want to decrease the probability of them failing. And then finally, the reduction of wind parks against market and generator plans reduces the efficiency in our grid and potentially could even lead to some penalties, financial ones. What is our solution to this? We want to first of all quantify the optimal active power demand and transportation potential, and then find an optimal infeed for all outage situations within 1 minute and automatically send the set points to the offshore wind parks. But how does the optimizer work itself? First of all, we consume the aforementioned grid models provided by the state estimation every minute. Next, we do a topology analysis and determine the maximum transportation potential. Then we calculate an AC optimal power flow to determine the optimal generator infeeds. We apply some post-processing, and then ideally in the future, we're not there yet, we send out controlled commands. But let me show you how that looks in the real system. So on the screen, you can see an example of our offshore wind park optimization solution. And essentially on the right-hand side, you can see the situation of the connection. So we are optimizing 2 offshore wind parks, Wikinger and Arkona Becken Süd. And as you can see, they are connected via 3 lines to the main, to the onshore. Now, the idea is, as I mentioned before, we consume state estimation and we calculate the optimal power flow or the optimal set points for our wind parks every minute. And this is what you can see here. So in the P-auto column, we provide the operators immediately the optimal set points that they can implement in the system without having to think about operational security. Because in the background, and that you can see in the table below, you can see that we are limiting the transported current over these lines to 100%. So we do not shoot over the maximum allowed capacity for these lines. Now, this is right now we have a quite normal situation. We have a lot of wind in feed, but all of the lines are there. So by definition, the optimizer does not need to do anything. But let's take a look what happens if one of these lines gets taken out of service, whether this is intentional or not. So we offer a simulation mode in our grid analysis tools, or especially here in the optimizer, which allows us to pretend that certain grid situations arose. For instance, I can go ahead and take the line 281, which is one of the main onshore cables, I can take it out of service. I would like you to pay attention to this P auto column here. I can start a simulation which pretends that this line is out of service, and then we can see what is going to happen to the system. So we're calculating two things. On the one hand, we are calculating the initial loading. What would happen if we wouldn't curtail the offshore wind parks? And here you can see that both of the other main lines are actually overloaded quite a lot. So 25% here and 30 here. But our optimization solution actually takes this into consideration. It is aware of the state that that the line 281 is out of service and will artificially decrease the infeed of our wind parks so we can reach these 100% line loading on the line 261. The result of that is that we cannot fully infeed all of the power that we could for Wikinger, but what we have achieved is operational security and also possibility for operators to not open a manual tool to calculate the set points and then type them into the SCADA system to implement those set points. Now, the applications here is currently on one wind park cluster. As I mentioned before, 2 offshore wind park groups are summarized here, but the Optimizer 2.0 in the future will also be used for upcoming wind parks that are either in planning or are being currently built. Now, we offer a lot of other features like changing certain configurations in terms of the optimization, but I will not go too much into detail about that. But let's quickly summarize what the optimizer does. So our offshore wind parks are not N-1 secure by definition. We calculate an optimal set point for our offshore wind parks every minute and therefore maintain operational security for our transmission grid. So much for the real-time optimization, and I will jump directly into the voltage optimization, our tool Volt Control, which is another example of our optimization backend, which we are currently developing. Volt Control. It is a software we are developing not only for 50 Hertz, but actually as a joint effort between 50 Hertz and Elia. And we want to ensure stable voltage or secure voltage level. For Elia, that means we want to operate the grid as close as possible to a target voltage. For 50 Hertz, it means more to keep the system within a designated range of voltages. So slightly different goals, but the tool is the same, and essentially we're working on the same software here. What is the challenge in general? I mean, you have all heard of the situation on the Iberian Peninsula, and I will address later how Volt Control could have played a role here. But we expect for our operators, especially in terms of voltage management, more actions due to the increased volatility that we have previously discussed on more units due to the decentralization. As you might know, voltage is a quite regional phenomenon, so we have to really take a look at not only what is there in the system, but where it is also. As an example, for 50 Hertz in the next years, we expect up to 60 measures for voltage management each hour. So that's 1 per minute. And you can imagine the joy of our operators when they hear about these kind of things or when they even think about these kind of things. Because it just simply shows the increased workload and potential for more critical solutions. Where's this coming from? Coal, to sum it up quickly, coal and nuclear phase out is arriving and high shares of renewables are pushing into the market and into the grids. And we have a higher and more volatile grid loading, not only in terms of current, but also voltages are experiencing these kind of oscillations on a very short time scale, but also on a larger time scale during the day. What do we want to provide as a solution for that? So step number 1 is we want to quantify the reactive power demand and potential during the entire day. We want to find an optimal combination of asset states during this day to reach our voltage objective that I just mentioned before. And very important, we want to maximize the free reactive power potential in our system. And that is the 3 main reasons or the 3 main tools that we want to implement in order to provide good solutions to our operators. But before I get into much detail, let's take a look at the software. I'm going to share the screen again. So let me briefly open our Volt Control solution, and this is what you are greeted with. And I've already pre-optimized a business day. It was at the end of March, to be exact, the 31st of March. And what you're usually greeted with, let me just briefly load here this optimization, is a typical voltage graph over a day. So you can see this is an unoptimized voltage profile of different substations in the Belgian grid. And you can see it's quite volatile. So in the morning hours between 6 and 10, we have a couple of peaks and dips. And in the evening hours, we have quite a large dip. Now, if we turn on the optimized values of these substations, so the voltage curves, you can see that we are much closer, first of all, much flatter, but also much closer to our target voltage of 405 kilovolt. So in short, our optimization has done what it should. So we want to be close to the target voltage, and we have decreased the volatility of our voltages in the grid. Now, what I need to tell you at this point in time, how does it work? So essentially, we use forecast grid models from both the intraday and day ahead processes, which usually contain one business day in an hourly resolution. Then we take those forecasted grid models, we calculate a time-coupled AC optimal power flow with the goal in mind that I just mentioned before. And finally, we provide the recommended countermeasures to our operators to help them manage the voltages across the grid efficiently. Now we are working on 15-minute intervals, which is also the basis for the market. But this is taking some time. So right now we are working on the hourly resolution. Let's take a look at some of the remedial actions that we are providing. So what you can see here are the transformer tabs of all of the transformers in the Belgian grid. You can quite clearly see a trend in the morning hours to switch up or tap up certain of these transformers. And then briefly after the voltage peaks have been flattened, they are being turned down again to really achieve a stable voltage profile over the day. I can show you the same for shunt elements. Again, we are providing for the entire day a clear overview of what needs to be done and when for our operators, so that they have essentially a forecast not only for loadings, which is currently the standard operational process, but also for voltages and especially the actions they have to take in order to take a clean or let's say secure voltage levels in the grid. Now addressing a question from the Slido briefly, how could the solution help at preventing something that happened in Spain? Now, with Volt Control, we're not aiming at really addressing short-term oscillations that might happen, but what one of the main goals of Volt Control is actually to provide the maximum amount of reactive power, which is free at any given time. So what that allows us to do is essentially to, at each moment in time, have as much reactive power as we need, or let's say, which could be beneficial for usage for voltage management. So this is a state that we want to achieve. We want to have the least amount of reactive power fed in at all times, therefore maximizing the potential that we can provide to the system in order to optimize the voltages. We can also discuss this a little bit more in detail later on, but that's my very short answer to the question in the Slido. We want to maximize the reactive power potential and therefore maximizing the ability to regulate voltages in the grid. But I think at this point in time, I will pass over to my colleague Christian Merz, who is also taking a look at forecast processes, but for a different type of phenomenon at this point in time. Thank you very much. And Christian, stage is yours.
Thank you very much, Dominique. So my name is Christian. I work as a product owner for the topology optimization product. Before we start, we've seen that there are a lot of questions on the Slido. We'll answer some at the end, and we'll definitely also answer every other question afterwards that we can then share. What I will talk about now is basically same setup as the others. So what are we doing? What is the reasons why we're doing it, and how we actually got to where we are now. So we look at topology optimization from a process overview. We look at operational planning. So this means we look at day ahead processes. So that means for the next 24 hours in advance. And what we're trying to solve is basically to reduce overloads within the grid. How would we like to do this? Basically, we want to use topological actions, especially we look at line switchings, busbar splitting, and busbar reassignments, which is the most complex of all of the potential options that you have. And why we want to do this, basically, we have in Germany, but also within Europe, very high redispatch costs. In Germany, we only talk about 2 to 4 billion of euros per year. And this is why every improvement that we can get, also with remedial actions, we look into. The optimization problem is very, very complex. Just looking at 50 Hertz, we have 10 to the power of 120 different possibilities. So what we have done over the last 2 years basically is to develop a very fast optimization algorithm. Arya also mentioned at the beginning that there were two main points that we are basing this on. One is collaboration and the other one is open source. If we look at collaboration, from the beginning, we were only very, very few people. So I'm talking here about 1 to 2 people working on this. So we exchange a lot with other TSOs and also research institutions. And that's how we actually built this very fast and scalable load flow solver that is running on DC. That is basically the core of the engine. And we developed together with, for example, Tenet Netherlands, also with other research institutions. And then we went step by step from grid planning data to historical operational data to now real operational data, and always improving the tool step by step in close collaboration with the operators. Where are we now? So basically, we have now a solution that I'll show in a second, also with an optimizer that provides a complete set of solutions. And basically there, what you can then see is that you can filter after the optimization on your constraints. I'll get to this in a second. Basically here, we can see the overall architecture of the topology optimizer. Also, you can see that we build heavily on open source, as our frameworks are PandaPower and Possible, two well-known grid analysis open source frameworks. Then we have some kind of pre-processing. In the middle, you can see the optimization solution that works on DC only, but we have included a lot of different features to actually propose solutions that different grid operators can actually use and are valid. And then to really confirm that all of the constraints that we have tested before are also relevant in AC, we do a validation step afterwards, pre-processes, and then show it in the UI. Talking about the UI, I will have a look at the tool itself. So I will share my screen. Just give me 1 second here. And we are here. So you should be able to see my screen here. Basically, it's the same setup as my colleague Dominique was showing before. We can select the different grid files, we can import them, and then we can run an optimization. I already have launched one optimization, which we can now have a look at. So basically, here we can see the different time steps. So as I said, 24 time step for the next day. I've selected now 3 different ones. At the beginning, you run initial load flows, so you can see the initial overloads at the beginning. And then you can run different optimization with different parameters. If we now look to the worst time step, we can now see here different strategies. What is a strategy? Basically, we define a strategy with a set of actions to take to improve the situation. And what we can then see here is that for especially the first one, we say, okay, after the optimization, we have a remaining overload of 500 megawatt. We have switching distance is basically the amount of steps that need to be taken to get to this new topology. And then we can see here the different substations that we look at to do the actions in. If we now click on one of these substations, we can look at the single line diagrams. Now you might wonder, what are the colors in here? Basically, the colors show the substations after the split. So what we want to do is basically want to redirect the electricity flow. And by splitting, as mentioned at the beginning, for example, the bus bars. And we can see it in the unsplit way. And also we can look at all of the different substations here, how they're being created. We can also look at the load flow results, the N-1 load after and before. And we can also export the results, for example, to other tools here, in this case, for example, to Power Factory to do any further validations. With this, what I would actually make two more Outlook topics. So this is the current as-is solution that we're working on. How would that look in a process? After you do the topology optimization, you would then potentially run a redispatch to solve the remaining overloads. What is also on the roadmap, what we're heavily working on. Basically, on the one hand, we do a lot of research on accelerated load flow solvers. This can either be new ways, novel methods from approximation, AI-based methods like graph neural networks, or other GPU-based methods. That's a lot what we're currently doing in collaboration with other TSOs, DSOs, and research institutes. If you're interested in this, more than happy to collaborate with you. Also, we have published several papers about this, which we can also share afterwards. And with this, I think I will give back the word to Arya. To summarize briefly here, again, what we've seen is the topology optimizer. Basically, we look at three different kinds of actions. And the fast advantage of it is using GPU-based optimization. And with this, I really pass now back to Arya.
Thank you. To summarize, and then we can have a few questions answered, and then we can move forward. But as we said, I mean, I want to emphasize we didn't speak about the first two parts, the strategy, the organization part. We focused today on the technology part and in specific the grid analysis suite. I also saw there was a question for outage planning, which is actually a product within our forecasting product line. But we will have another session on this one. Generally, I want to emphasize the ecosystem approach. We really, if you are interested, if you're working on something similar in your organization, Christian mentioned it already, open source, co-creating different modules, exchanging ideas, please reach out to us on our website. And also, if you're interested to join this journey, we have many open positions, to be honest, from development side, electrical engineering side. So we really look forward to have a lot of people engaging with us. And with that, I would use the last 5 minutes for some questions. I'm looking here at my colleagues in Berlin. I think we have some questions on the voltage part, and we also have some questions on the state estimator part. Do you want to start, Dominique?
Yes. So quickly on the Spanish outage topic was briefly addressed. What is the time span over which the analysis tools run? 24 hours longer. At the current time, it's 24 hours with a granularity of an hour. So we are basically depending on the European or the data sets which are being sent out for the European congestion processes. So mostly calculating on IGN's individual grid models of these processes. Let me just see here. Is the voltage optimization tool addressing post-contingency voltage violations or exclusively addressing pre-contingency voltage level targets? That's a nice question. So we plan on doing both. So at this current moment in time, the next step that we're going to do is also hook up a contingency analysis based on our countermeasures. That means all of the actions that we define will be checked for the N-1 criteria. But then in the future, also depending on performance and available hardware and many other topics, we can think about an N-1 optimization. Obviously, this will increase the complexity of our equation system by a lot, and it also will cause a lot more topics on robustness, I would say. So while it is definitely a plan to consider post-contingency voltages, right now we are not optimizing for them, but only analyzing our results, or let's say the actions that we are calculating based on the N-1 criterion. And then maybe a last one, what is the difference between Volt Control 50 Hertz and Volt Control Elia? Those are just two instances of the same software, which have different data streams coming in the front. So one is coming from the Belgian forecast system, and one is coming from the 50 Hertz grid calculation software. But essentially, it is exactly the same instance and also same backend, same logic. The objective function of our optimization is slightly different, but overall, we are using the exact same tool here. I just saw one voltage in the network can be controlled by reactive power coming from various devices connected. Is the MCCS connected to the market where Q can be procured? I would say not directly, but what we will be doing is to provide actions for the Q market. That means, for instance, reactive power from DSOs. This is currently in development or has recently been deployed in Germany, where you can ask for reactive power also at the infeed points of the DSOs, and we will consider this in the optimization. Nevertheless, this will still take some time because the entire market is still developing as well. And I think maybe I can pass to Christian as well for some comments on the questions.
Yes.
We're going to have to wrap up in just a minute or two, so we're not going to have time to go through all the questions. We'll start losing people at the top of the hour, but I did see one question in there that I thought we might do a quick round robin on, or maybe somebody has some thoughts about the use of AI techniques in any of the tools that you're using. Anybody want to take a stab at that?
Yeah, sure. I can definitely take some words on that. Yes, so indeed, we are looking into a lot of different approaches. Basically, our main vision is, or main approach is, we need to solve the problem, and the process or the tool doesn't really matter. If we can use AI, great. If we can use standard method, also fine. Mainly, we are investigating a lot, as I was mentioning earlier, in regards to the load flow solver and the optimization engines. So we also experimented with reinforcement learning at the beginning. Also for the topology optimization, there's a huge track around reinforcement learning around this. Also for load flow solver, we look at GNNs, so graph neural networks. So there are different approaches that we look at, and we definitely also have a complete product team that will work or is working on AI-based grid analysis. And this will then also be integrated or is already integrated in one of the several projects.
We've certainly been thinking about it. Any last thoughts before we have to wrap it up?
No, please reach out to us. Thank you very much. It's always great to be here, Charlie, with G-PST and ESIG, and we really appreciate this opportunity, and we look forward to many, many more formats like this to exchange with our peers around the world.
Okay, great. I really want to thank you, Arya, and the rest of the team for sharing these insights with us today. This is really groundbreaking work that you're doing. I think it's going to serve as a source of inspiration and ideas for a lot of work yet to come. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. So for everyone, we really appreciate your participation. And if you'd like to stay engaged, I'd like to invite you to participate in the next 2 ESIG webinars this week on a flexible solar interconnection demonstration out of OnGrid on Wednesday, and the impact of data center load on turbine generator shaft torsional vibrations on Thursday. And if that's not enough, I invite you to attend the ESIG Fall Technical Workshop, which will be held in Philadelphia the following week. There's still time to register, and no worries, you'll still be able to get home in time for Halloween. So further information on these and all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. So Arya, I want to thank you and your team once again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. See you soon.
Thank you.
Thank you.